Training a model gets all the headlines, but the part you actually pay for every single day is inference. So, which is running the model to generate text. It is also where most of the engineering effort goes into, because making a model fast and cheap to serve is brutally hard. Over the next few minutes, we look at what really happens when a model answers you, the two phases of generation, the KV cache that makes it possible, how batching squeezes a GPU, and the tricks like speculative decoding that make tokens come out faster. Generation happens in two very different phases. First is prefill. The model reads your entire prompt at once, processing all those tokens in parallel to build up its internal state. This is fast and uses the GPU heavily because everything happens together. Then comes decode. The model produces the answer one token at a time. It generates a token, feeds it back in, generates the text, and repeats. Decode is sequential and cannot be parallelized across the answer because each token depends on the one before it. Understanding this split matters because prefill and decode have completely different performance characteristics, and almost every optimization targets one or the other. Here is the single most important optimization in inference, the KV cache. Recall that attention turns each token into a key and a value. When generating token 100, the model needs the keys and values of all 99 tokens before it. Without a cache, it would recompute them from scratch every single step, which is enormous wasted work. So instead, the model computes each token's key and value once and stores them. Each new step only computes a new token and reuses everything cached. This turns generation from quadratic recomputation into a cheap incremental step. The KV cache is what makes token by token generation practical at all. The KV cache buys speed, but it costs memory, and that becomes the real bottleneck. The cache grows with every token, for every layer, for every attention head, for every request you serve at once. A long conversation with a big model can need many GBs just for its cache, on top of the actual model weights. This is why context length is expensive and why a GPU runs out of room serving many users. It also reveals something surprising. Decode is usually limited not by compute but by memory bandwidth, the speed of shuttling all that cache data in and out. The GPU often sits waiting on memory, not the actual math. Since decode leaves the GPU waiting, the fix is to keep it busy with many requests at once. That is batching. Process multiple users' tokens together in one pass, sharing the cost of loading the weights. Naive static batching has a flaw though. Requests finish at different times. So the whole batch waits for the slowest one while finished slots sit idle. Continuous batching actually solves this issue. As soon as one request finishes, a new one takes its place in the batch immediately, with no waiting for the actual group to complete. The GPU stays packed. This one single idea can multiply how many requests a server handles, and it is standard in modern inference engine. Continuous batching creates a new headache, managing all those KV caches of different growing sizes. Reserving a fixed big block per request waste a huge amounts of memory because most requests are short. Paged attention, the idea behind the VLLM engine, borrows a trick from operating systems. Instead of one contiguous block, it splits each KV cache into small fixed size pages, allocated on demand and tracked by a table. Memory gets used only as a request actually grows, and fragmentation nearly disappears. The payoff is that you fit far more concurrent requests on the same GPU, which directly raises throughput. It is virtual memory, but applied to attention. Decode is sequential, one token per step, which feels like a hard limit. Speculative decoding sidesteps it. Use a small, fast draft model to guess the next several tokens cheaply. Then the big model checks all those guesses in a single forward pass, the kind of parallel work it is good at. Every guess the big model agrees with is accepted for free, and the first wrong one is corrected. When the draft is right often, which it usually is for easy stretches of text, you get several tokens for the cost of roughly one big model step. Same output, just produced faster. It is verify in parallel instead of generating one by one. Quantization helps inference twice over. Storing weights in fewer bits, say 4 or 8 instead of 16, shrinks the model so it fits on smaller or fewer GPUs. But it also speeds up decode, and here is the non-obvious reason. Since decode is bottlenecked by memory bandwidth, moving smaller weights through memory is simply faster. So the model generates tokens quicker even when the math is unchanged. The trade-off is precision. Too aggressive and quality drops. Modern methods are careful about which parts to compress and how, keeping the sensitive bits more precise so you get most of the speed and memory savings with little visible loss. Finally, the tension that shapes every serving decision: latency versus throughput. Latency is how fast one user gets their answer, often measured as time to the first token and the gap between tokens. Throughput is how many tokens the whole system produces per second across all users. These pull against each other. Bigger batches raises throughput, lowering cost per token, but each individual request may wait a little longer. A chat app optimizes for low latency so it feels snappy. A bulk processing job optimizes for throughput to minimize cost. There is no single best setting, only the right balance for your use case, tuned with the tools we just covered. So that is inference end to end. Generation splits into a parallel prefill and a sequential decode. The KV cache stores keys and values, so each token is cheap, but it eats memory and makes decode memory bound. Continuous batching keeps the GPU full, paged attention manages the cache efficiently, and speculative decoding produces several tokens per step. Quantization shrinks the model and speeds it up by moving less data, and every real deployment tunes the balance between latency and throughput. Training builds the model once, inference is what you run forever. And this is how it is made fast. Hope that answered how inference works. If you have any questions, let me know in the comments.